Magnets. Everybody knows the that there are two types of magnets. We have the electromagnet, which is like a temporary magnet. Then we have the permanent magnet, and we saw the uses of them. Permanent magnets are used for things that you need to keep doing. You need the magnet to do over and over again. We need it to be a campus. We use it in a campus. We use it in school experiments because we will need to use it over and over and over and over and over again. We need it on the fridge magnets to attach things to the fridge, like important recipes or things, whatever. And then we have the electromagnet, which is important as well. It is the one which is made by electricity. So if we want to make a magnet which is temporary, one which you can make it magnetic, you can switch it on and switch it off, then we use electricity to do that. You don't have to know how. At this age, you don't have to know how. All you have to know is that it's there and we can use it. So don't try to focus on learning how. That's not what is expected of you. They expect you to know the uses of electromagnets, if anything. What are the uses of electromagnets? So you must supposed to know, and we put a lot of the uses, important uses. Everything that produces sound that captures and produces sound. So from a microphone, like the one I'm using, and speakers, the one you all have, or earphones, right? All of them have temporary. Don't say temporary though. Say electromagnets. All of them have electromagnets. So that's important, the uses. The other thing which is very important is for you to understand this word, which now needs to be part of your vocabulary, physics vocabulary, magnetic material. So, what is the difference between a magnet and a magnetic material? We'll write it down just now. When something is called a magnetic material, it means it's something that is always attracted to a magnet. Whether you spin it and spin it and spin it, that doesn't change anything. It's always attracted to a magnet. Period. There's no other definition. I don't want to hear it. Magnetic materials are materials that are always attracted to magnets, or only attracted to magnets. They cannot be repelled from magnets. Examples, we had the ICN. You should know them. Iron, cobalt, nickel. The most important one is iron. Things that have iron are actually called ferrous substances. They are attracted to a magnet. Iron, because iron is Fe, so they say ferrous to mean things that have Fe in them. This is a magnetic material, meaning to say that it is always attracted to a magnet. All the time. You put a magnet close to iron, it is going to move towards the magnet. Period. So don't forget magnetic materials, please. Are we together? Then we have materials that are non-magnetic. They never get attracted. They don't get repelled. They don't get attracted. They just ignore magnets. They don't even move. Whether you put a magnet close to it, far from it, whatever, it has no relationship with the magnet. Okay? These are not attracted to magnets. Neither are they repelled by magnets or from magnets. Aluminium, copper, zinc, silver, gold, magnesium. Look at all these metals. Obviously, non-metals, we don't even have to put them. They will never move. But we're talking about metals. They're the ones who may be attracted or may not be. When we say it's non-magnetic, it will be a metal that is not attracted. They are not attracted to magnets. They have no relationship with magnets. Look at this list and remember it. These people, these things, these metals have no relationships with magnets. Are we together, students? Are we together? Now, you should just write this. Difference between a magnetic, I've already said it. Well, you should just write it. difference between a magnetic material and a magnet is that a magnetic material, sorry, let me do that. Can you see my screen nicely? Students? Tobo, can you see my screen nicely? The difference is this. Write it down. Okay, I wanted to text the group to make them join. Is that a magnetic material is attracted. There is no repulsion here. It is attracted to both. Don't forget this. Don't let me down. It's attracted to both poles of a magnet. If you bring the south pole, it's attracted. If you bring the north pole, it's attracted. It's not picky. It's not like a magnet. A magnet is only attracted to one pole, whilst magnets are attracted to one pole and repelled by the other. We know that. We know that. If the side of a magnet is south, then it would be repelled by another south. But if you turn this one around to make it north-south, then it's now attracted. So it's attracted to one side and it is repelled by the other. Are we together, students? Students, are we together? So, what I want you to know is that when we talk about temporary magnets, the name that they may like to use instead of electromagnet is induced magnet. And there's some things that they may need you to know. Let me put it for you right now. Something that is important. Okay. Let me write it, or let me give it to you. Should I give it to you? Okay. Let me just put one part first. Let me first teach you this. Okay, so I'm keeping it minimal. I don't want to over explain anything. We need to move and finish. And I want to give you things that you may be asked on. I want you to write. So magnets, electricity, gravity, they work like together. They work in a similar way. They can work without being in contact. Right. Why they do that is, let me tell you something. This is planet Earth. People stay on the surface. If you have a person who is here, they are in the atmosphere. Now, if they are close enough to planet Earth, if they were to fall, they would not fall like this. No, no, no. They would be falling like this until they crash onto the ground. So they would come and hit onto the ground. Why? It's because they will be pulled by the force of gravity of the earth, which wants them to get to the center. Force of gravity of the earth pulls you from the inside. But we know you can't get into the inside. That's why you will hit onto the surface. So it wanted you to get inside, but you cannot get inside. So you hit onto the surface, and we call it a crash. Right. So the reason why you were falling like this is you are in what we call the field, the magnetic, the gravitational field of the earth. You are in what they call the gravitational field of the earth. Let's say you are an astronaut. You have a very powerful rocket, and you go away from earth and keep going until you go somewhere here. If your engine fails, my friend, you are not falling back on earth. You will fall somewhere else in space. It's because you are now out of the field. So these forces, like a magnet, if you go very far from a magnet, it will stop working. But if you put a material close to the magnet, then it will be pulled. If you put a magnetic material close to the magnet, it will be pulled. It's because it's in the field. So we want to try and understand the field, which means the area around the magnet where it has power. We know that it works. It's a non-contact thing. We don't need this individual to be in contact with the earth. No. They can be in the atmosphere, but they will be pulled by the earth because they are in the field of the earth. That's how field forces work. Non-contact forces are also called field forces. What are they? Gravity, magnetism, electricity. You have to be close enough, then they will work on you. You have to be in their field, then they will pull you. Without any contact, you just have to be in their region, then they work. If you go outside their region, then it won't work. Are we together? So magnetic fields, they want us to know the areas around a magnet where it has power. Do you understand, students? They want you to know the areas around the magnet where this magnet will be having power. So you need to know the shapes. When you change the shape of the magnet, you can change the shape of the area where it has power. If you change we need to see, how do you make a magnet stronger? What is it that you can do to make the magnet stronger? That's important. So the fields, you have to know the fields. Are you ready to draw with me the fields? So let's first write what it is. Then we start drawing the fields that you are supposed to know. Okay? What is the field? The region. Let's write it. But it's just the area where the magnet works. You hear me? So write with me to say, that's all they want you to know in this section. Don't let me down. You should know the fields. For this shape, the field is like this. For this, it's like this. The region in which a magnetic material will experience a force, or a magnetic pole. They write it like this. A magnetic field is a region in which a magnetic pole experiences a force. Okay, everybody? Why do they say the word pole? We know that pole is just the end of a magnet, and it's where the magnet is really strong. So basically, we know that if you bring a magnet close to another magnet, they will act on each other. And where will they be acting? Here at the poles, because that's where the magnetism really is there. Poles means the ends. So if you bring the end of a magnet or a pole close to a magnet, they will start working on each other. But that only happens if you enter the region around one magnet. So it is a region in which a magnetic pole, in other words, it is a region in which another magnet will experience a force once it enters. But we're not talking about the center of the magnet where there is nothing. We're talking about the ends. So you should write it the way they want you to write it. It is the region in which a pole, a magnetic pole, experiences a force once it enters. Are we together? Students, are we together? Now let's do the fields you need to know. 1. Magnetic field. They ask these type of questions around a bar magnet. What is the region where that a bar magnet will work? What is the region that the bar magnet will make another magnet experience it? What is the region like around a bar magnet? I taught you that a bar magnet is a magnet that's a bar. And a magnet that's a bar, north, south. What does it have? What would it have? So, let me tell you some rules. Okay? Magnetic field lines always come out of north and they go to south. So when you're drawing for your bar magnet, you must show the field lines coming from the north pole, okay, which is the tip of the magnet, and going to the south pole. So put your arrows correctly. And they will be bending. So this is the easiest thing. You do a second one nicely, going from north to south. We know that for electricity, it's from positive to negative. For magnets, it's from north pole to south pole. Have I made myself clear, students? Can you all see this? And you must show one which goes like this. Just put an arrow like this and show it now arriving. It's because it did a long journey like this. So you should show it just like that. They come out of the north, they go to the south. Okay? This is the field line around a bar magnet. Are we together? Hello? Laura? Are we together? These are the fields around a bar magnet. Now, what you must know is that when you have more field lines closer to each other, you have a very strong field. If there are a few of them like this and they're spaced out, you have a very weak field. Okay? And we already know that when we deal with our field, when you are close to the poles, it's very strong. That's why the magnet is stronger. And it gets weaker as you move away. So, let's just write these some words here that I need. How do field lines show strength? You should say, when field lines are close together, then the magnetic field is strong. When field lines are far apart, then the magnetic field is weak. We have a weak field when they are far apart. You know this. I'm just writing for the time you may need them. Okay? Now, here will be the rules to remember when you will draw field lines. Rules for drawing field lines. Rule number 1. Outside the magnet, field lines travel north to south. Don't let me down. May I not see weird stuff? They come out of the North Pole and they get into the South Pole. Put your arrows correctly. Okay? Field lines must have arrows. Don't leave out the arrows. And they point from north to south. Okay? Okay, in brackets say the arrows show the direction of magnetic force. Are we together? Are we together? Right. Now let's do the second type of field lines you need to know. You need to know only 2 types. Everybody has seen the field around a bar magnet, right? Now, I want you to now say magnetic field lines between 2 bar magnets. When you have 2 bar magnets, what type of field lines do you have? How do you draw? You should be able to draw this. 1, 2 attracting bar magnets. How do we draw field lines between 2 bar magnets that are attracting each other? Here's one. Here's another. North and south, okay? The only way they attract is when they have opposite poles. We already know that. Now, so what do you know when you're drawing these field lines? You know that they already must be coming into south, leaving the north. So now we have between 2. I don't want to see them do this now. Here's what they now do. They come from this north and go to this south. So it's like this. Put the arrows. Don't leave the arrows. Then put like this. North to south. North to south. Okay? Now, don't say Mr. Clarify didn't tell you that. When you check the videos on YouTube on magnetic fields, I remember them from many years ago. You should also know that it's true. Field lines, they don't stop. They actually go around. They connect like this. But we just don't show it, okay? They are continuous. But we don't show them continuing inside the magnet. We just end. But what you must know is that field lines are continuous. So if somebody tells it, don't Don't say Mr. Clarify never told me. It's nothing. That's not big news there. To say fluid lines are, it's true, you must know that, but then you don't put it on the diagram. So you leave it like this. Don't show the fluid lines inside the magnet. But remember, they are actually, in reality, they are continuous. Here's what you just do. You do it like this and you leave the gaps. Can you see the field lines between two magnets that are attracting? They bring a north pole and a south pole. Can you see that? And this one now, you'll be now showing some fields coming out of the north pole. Okay, this is how you draw the diagram. Like this, coming out of the north pole. And here you can show it like this, coming out of the north pole. They should be coming out of the north pole. Here you should show them coming into the south pole. The same diagram, but in the same curves, one straight line, another curve, but now they are coming into the south because they come from north to south. Don't forget. And these two poles will be made to attract. They are opposite. One is north, the other one is south. Have you seen? Now, here's how you draw field lines between two repelling bar magnets. You now need to draw field lines between two bar magnets that are repelling each other. They don't like each other. Now, why are they repelling each other? Because you brought the same poles together. And magnetism has a rule that says like poles repel. So you bring two bar magnets, and it's a north and a north. Ooh, then we have a problem. Or it could be a south and a south, doesn't matter. What we want to see, it usually happens for north and north. We want to see the fields running away from each other. These things are repelling, so we want to see them do this. Okay, arrows come out of north. So remember, your arrows will be showing that the lines are coming out of north. So that's not a problem. So you do it like this. Then you show them getting into south. Questions? These are two repelling bar magnets. What I need you to know is that if you go to this region here, between two repelling bar magnets, this is a region of zero force. But if you come here, you have a uniform field, and what you'll be having is the strongest point. Strong magnetic field. Okay? Now, if they want you to show strength, remember you just draw a diagram with more lines, but just the same design, curving outwards or whatever. Just put more lines, then you'll be having a stronger field. Are we together? Okay? Don't remember, but don't forget, always show, always put arrows, okay? Let me put my tips here. Always, okay? Tips. Always put arrows, okay? You lose marks for not doing that. Show that they are coming from north. Always, okay? And remember, field lines show strength. Remember, field lines show strength. Are we together? One more thing, which we'll do next time, will be I'll need to teach you this time out how to now uh, plot magnetic field lines. Okay, uh, using the compass or iron filings, the practical methods. Then we write those practical methods. You need to know them. Okay, and then you have good. I should just give you the steps, the procedure. Basically, you should know the procedure to see. Okay, you're going to put a paper over a magnet, then you sprinkle some iron filings, blah 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 blah, and you'll be done. And you'll be fine. You'll be fine. So I'll teach you how to find out the direction of your magnetic field using iron filings. You should know how to use iron filings over a magnet, or I'll teach you how you use a compass. That's not a problem. We'll be fine. I'll teach you that in the next lesson, and you'll be done with magnetism. Then I'll teach you how a generator works, a motor works, and a transformer, how a transformer works. And now we'll do calculation questions, and you are not going to let me down. No, you're not. So all these things, you should put them in your head. I'll give you a bunch of questions from this. I have to now, soon as the lesson finishes. Okay? Okay, my good students. We're together. Good. Well done. Let's do a bit of chemistry.